Ladies and gentlemen, welcome to Secrets of the Unit Circle. If you're anything like me, early on in your mathematical journey, you were told to memorize the unit circle. Well, how hard can that be? Yeah, I'm not memorizing that. You know what? It's fine. It'll go away in my next class. But it didn't go away. Well, that probably means that it might be important. Hmm. How on earth am I supposed to memorize all of these values? Well, instead of trying to brute force to memorize all of the values that you see here, it might be a better idea to try to use your pattern recognition skills to identify what patterns are going on where. And that way you can use logic to construct a unit circle from scratch. If you go and you look up unit circle, this is like the first thing that comes up. And this is pretty intimidating, but you know what? Let's just break it down. You got your x coordinate here, and you got your y coordinate here. X, Y, X, Y, and such is true throughout the entirety of this. The equation for the unit circle is x squared plus y squared equals 1. So you got your x here and you got your y here. Now, when it comes to the unit circle, the x coordinate is always going to be cosine, and the y coordinate is always going to be sine. Well, I've just generated a circle. Let's put some lines through it. This is not going to be perfect. Typically, your unit circle is going to have a point here, a point here, a point here, a point here, and then in these sectors, there's going to be three, three in between each. And like I said, you guys, this is not going to be perfect, but let's just, just give me some grace, all right? Um, Now, you might notice that there could be an extra point in between here and in between here, but we're not going to bother with those right now. All right, let's try to divvy this up the best we can. I mean, okay, look. We all know how to draw a circle and we all know how to draw lines through it. Now, let's use our pattern recognition skills to construct an actual unit circle. I'm not so concerned right now with the degrees. I'm more so concerned with the radians. Because if we have the placement of the radians, then we know how to get the degrees. To get the angle in radians, you do pi over 80 times the degrees, and then that's how you get the radians. And the inverse is true if you're trying to get the angle in degrees. I want to start using this template and counting upwards by counting upwards starting at 0 over 12 pi. So instead of 0, we're going to have 0 over 12 pi. Now we're just going to start counting upwards. Now you might notice that there is a missing line here, right? We could put a line here, all right? And if we did, this would be 1 pi over 12. Let's just count upwards. This is going to be 2 pi over 12. Wait, but there's another way to write this. We can simplify this. And if we simplified it, well, it's going to be pi over 6. Does that look familiar? Well, it should because there's pi over 6 right over here. Let's just keep counting upwards. 2 pi over 12. Well, let's put 3 pi over 12. Well, we can simplify this fraction. If we simplify this fraction, it's going to be pi over 4. Just like how we have pi over 4 over here. Let's continue to count upwards. 3 pi over 12. Well, if we count upwards, we're going to get 4 pi over 12. 4 pi over 12 can be simplified to pi over 3. Now, before we jump to this radian here, let's just acknowledge that there is technically a line here that's invisible that is not put on most unit circles, interestingly enough. But if we went from 4 pi over 12 to 5 pi over 12, well, that's where that would be. Then we can jump to right here, and then this is actually going to be 6 pi over 12, also known as 1/2 or pi over 2. 1/2 pi or pi over 2. All right, and that's going to be over here. And I'm not sure why they don't put the line here, but conveniently enough, its absence hides the pattern. But this is the secrets of the unit circle, guys, so we're going to keep going. 6 pi over 12. Now we got 7 pi over 12. All right, and then 7 pi over 12. Well, now we can keep counting upwards. This is going to be 8 pi over 12. 8 pi over 12. And we could simplify 8 pi over 12 to 2 pi over 3. This is 9 pi over 12. The 9 pi over 12 can be simplified to 3 pi over 4. And I would just like to point out again that all of these values, they're present on they're present on the unit circle. Pi over 6, pi over 6, pi over 4, pi over 4, pi over 3, pi over 3, pi over 2, pi over 2, 2 pi over 3, 2 pi over 3, 3 pi over 4, 3 pi over 4. Next up, we got 10 pi over 12. Oh, well, that's the same thing as 5 pi over 6 upon simplification. Um, we have our absent line here, which would be 11 pi over 12. All right, then we can make that jump a little bit more swiftly because this is going to be 12 pi over 12, also known as 1 pi or just pi. Right, and we'll just put a little comma there. And then we have our absent line, which is going to be 13 pi over 12. And then if we keep going, this is going to be 14 pi over 12, which can be simplified to 7 pi over 6. Fourteen pi over 12. Let's go to 15 pi over 12. Well, 15 pi over 12 is the same thing as 5 pi over 4. Then we'll go from 15 pi over 12 to 16 pi over 12. And 16 pi over 12 simplifies to 4 pi over 3. And we'll put our invisible line here, which would be, I mean, it's technically there, it's just not drawn in for most unit circles, but it's going to be 17 pi over 12. And that reveals to us that this is going to be 18 pi over 12, which when simplified turns into, and maybe I shouldn't put a comma, maybe I should put an equal sign. If we simplify this fraction, it's going to be 3 pi over 2. And I'm going to write an equal sign. And for the sake of consistency, 0 pi over 12 is 0. 18 pi over 12, well, if we draw in our missing line between these two, this is going to be 19 pi over 12. Then we can make the jump. This is going to be 20 pi over 12, which is the same thing as 5 pi over 3. And then we're going to go to 21 pi over 12. 21 pi over 12, it's the same thing as 7 pi over 4. 21 pi over 12. We're going to move over to 22 pi over 12. We're going to hit it with a simplification, 11 pi over 6. All right, we're going to draw in our line that's absent so we can smoothly make the transition. Let's see, 22 pi over 12, that's going to bring us to 23 pi over 12. All right, that's how you can create your unit circle from scratch relative to the radians measurements. And then if you have the radians measurements, if you have the measurements for radians, then you can get the angles and degrees as well using our simple conversion formulas. The only thing left to do is figure out how are we going to get these x and y coordinates here. Remember, here is the x coordinate and here's the y coordinate. How are we supposed to get these throughout the entire circle for all of these values? Well, let me show you how. The only reason that I left this up in the first place was to show you guys how you could derive the radians from counting up the fraction of 12. That's the only reason I left this here. We could just get rid of it for now until we're ready to do another side by side so I can use a proof to show you guys how to get the coordinates. The reason also is because I need more room over here to show you guys the trick on how to get the coordinates. I don't know about you guys, but maybe you've seen somebody working on some sort of calculus problem, right? And they find themselves evaluating sine of pi over 6. And then they're like, oh, so sine pi over 6, right? That's the same as 1/2. And you're like, what? How did you know that? What do you mean sine of pi over 6 is the same as 1/2? Like, where's the logic? And then they turn to you and they go, oh, well, it's special angles. As if that's some sort of answer to the question that you've asked. And you say, special angles, what is that? And they're like, well, those are the angles that you have to remember. You go online and you see a table like this, and you're like, dude, what? And then it shows you, like, okay, like if you have like sine of angle theta, and angle theta is pi over 6, well, then that means that the value that you're going to get for that is 1/2, right? Or if you have cosine of 2 pi, right? Then the angle that you're going to get for that, or then the answer you're going to get for that is 0. And you're like, what do you mean memorize that? Well, let me show you how to memorize that. We'll set angle theta to the special angles that we're expected to know. This includes 0, pi over 6, pi over 4, pi over 3, and pi over 2. So how do we find our cosine values, our cosine coordinates? Let's count down from 4. 4, 3, 2, 1, 0. So we have 4 over 4, and then we're going to put a radical over that. Well, what's the square root of 4? Oh, that's 2. What's the square root of 4 again in the denominator? Oh, that's 2. And now maybe it's easier to see that this is going to be 1. All right. We got 3 over 4 with a radical over it. What's the square root of 3? Square root of 3 is just going to be the square root of 3. What's the square root of 4? 2. What about this 2 here? Well, we'll put that over 4. That's going to be consistent throughout. So then what's the square root of 2? The square root of 2 is root 2. What's the square root of 4? Or the square root of 4 is just 2. All right, let's follow suit down here. The denominator is gonna stay 4 for all of these guys. We got the square root of 1/4. What's the square root of the numerator? Well, the square root of 1 is just 1. What's the square root of 4? The square root of 4 is 2. 0 over 4, the square root of 0 over 4. Well, that's just this whole thing is just gonna go to 0. So, square root of 0 is 0. Square root of 4 is 2. 0 divided by 2 is 0. But now we have to do sine. Well, instead of counting down like we did for cosine, 4, 3, 2, 1, 0, we're going to count up from 0. 0, 1, 2, 3, and 4. The denominator for all of these is going to be 4. Say the square root of 0 is 0. The square root of 4 is 2. But this is just going to go to 0. And now we want to take the square root of 1/4. Well, the square root of 1 is 1. The square root of 2, excuse me, the square root of 4 is 2. So we have 1/2. We have 2 over 4. Okay, what's the square root of 2? The square root of 2 is just going to be root 2. What's the square root of 4? The square root of 4 is 2. So we have root 2 over 2. 3 over 4. Take the square root of that. What's the square root of 3? Well, the square root of 3 is root 3. What's the square root of 4? 2. The square root of 4 over 4. This is going to be 2 over 2. That's the same thing as 1. Now we have our y coordinates. And just like that, we have our special angle table. All right, so I'm going to move our unit circle over here. I think that now at this point I've proved that we've recreated the same values on the unit circle. So I'm just going to clean this up. Now let's use our special angle table to reveal to us what the coordinates are on the unit circle. Because remember, we have the radians, right? But we need the coordinates. Well, where do I begin? Pi over 6. Pi over 6. What are the coordinates for pi over 6? Well, we're going to start with our x coordinate. Cosine is x. And then we'll go down to pi over 6. Okay, so it looks like for cosine, or the x coordinate, pi over 6 is equal to root 3 over 2. But what about for the y coordinate? The y coordinate is sine. So let's look at sine. Let's go to pi over 6. And the table reveals to us that the y coordinate is 1/2. Is this correct? Is the x coordinate root 3 over 2 and the y coordinate 1/2? Root 3 over 2 and 1/2. Nice. Okay, let's do the next one. Pi over 4. Well, we need the x coordinate for pi over 4, so let's look at cosine pi over 4 root 2 over 2. Okay, what about the y coordinate? Well, we're looking at pi over 4. That's going to be a root 2 over 2. Both of them are root 2 over 2. Let's just check. Nice. Let's do the next one. Pi over 3. Well, the cosine x value, pi over 3, is 1/2. What about the y value? Root 3 over 2. And then we're just going to skip over this 5 pi over 12 because remember, that's not on the unit circle. It would be right here if it was, but it's not. I mean, it technically is, you just can't see it. Most people don't really bother with those. What about pi over 2? Let's find the x-coordinate for pi over 2. The x-coordinate is 0. Okay. And what about the y-coordinate? Pi over 2. Oh, it's 1. So 0, 1. Nice. Okay, well, at this point it gets a little bit more tricky. We have to up the ante, right? It would seem that our luck has run dry because, well, if I look at our next, remember we're going to skip 7 pi over 12. But let's say we want to recover these coordinates here in the second quadrant. Remember, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. This is quadrant 1, quadrant 2, this is quadrant 3, this is quadrant 4. I don't want to actually draw on the circle because I don't want to make it more complex than it has to be, but we do need to know our quadrants for this next part. So the thing is, right, to recover the x and y coordinates for any angle in quadrants 2, 3, and 4, you just look at the reference angle in quadrant 1, and then look up those coordinates, and then apply the correct positive or negative signs. For quadrant 2, the reference angle is found by doing pi minus the angle. For quadrant 3, the reference angle is found by doing the angle minus pi. For quadrant 4, the reference angle is found by doing 2 pi minus the angle. And there's a couple of more rules. For quadrant 2, once we find the reference angle, we can just copy and paste its coordinates, but we have to change x to a negative sign. For quadrant 3, we can take the coordinates from the reference angle, which is in quadrant 1, but we have to change both the x and the y to negatives. For quadrant 4, we can take the coordinates from the reference angle in quadrant 1, we just have to apply a negative sign to the y coordinate. So that's what this means. When it comes to remembering quadrant signs, some people use the mnemonic device ASTC, and that means A in the first quadrant, all signs are positive. S for the second quadrant, only sign is positive. T in the third quadrant, only tangent is positive. And then C in the fourth quadrant, only cosine is positive. We only have the coordinates for the first quadrant. Well, that's not cool because we don't have any of the coordinates for the second, third, and fourth quadrant. So allow me to show you how we can recover those coordinates. So for example, let's say that we want to find the coordinates for 2 pi over 3, which is in the third quadrant. The first thing that we have to do is find its reference angle. And to find its reference angle, what we need to do is put a comma here. We're going to subtract it from pi. So we're going to do pi minus 2 pi over 3. Now, pi is the same thing as 3 pi over 3 because it's just 1 pi. And we'll subtract our angle. 2 pi over 3, and that's going to leave us with pi over 3. Pi over 3 is right over here in the first quadrant. That's our reference angle. So I'm going to mark our reference angle right here, and I'm going to connect it to the coordinates that we want to find. So if we look at the coordinates for pi over 3 radians, I can see that the x-coordinate is 1/2 and that the y-coordinate is root 3 over 2. Now I can steal these coordinates and put them over here, but I have to check the rule first. Well, the rule is that the x needs to be negative and the y needs to be positive. Okay, so we'll make the x negative, meaning that we're going to have negative 1/2, and the y can stay positive, so it's going to be root 3 over 2. All right, so our coordinates are negative 1/2 for x, and then y is root 3 over 2. Let's just check to make sure that's correct for 2 pi over 3. 2 pi over 3, negative 1/2 for the x-coordinate, and positive root 3 over 2 for the y-coordinate. So we got that. Let's do another example. Let's say that we want to find 5 pi over 4. Well, 5 pi over 4, let's see, this is right here. A 5 pi over 4, that's in the third quadrant. And the rule for the third quadrant is that the reference angle is found by taking the original angle, in this case 5 pi over 4, and subtracting pi from it. So we're going to subtract pi from this. And if we subtract pi from 5 pi over 4, we're going to get pi over 4. Pi over 4 is right over here, so this is our reference angle. So pi over 4 is our reference angle, and the x-coordinate is root 2 over 2, and then for the x-coordinate and for the y-coordinate, it's also root 2 over 2. However, for quadrant 3, we have to apply the quadrant 3 sign rule, which means that both of them are negative. So the coordinate points, the x and y coordinate points for 5 pi over 4, it's going to be negative root 2 over 2 for the x, and then for the y, negative root 2 over 2. And those are our coordinate points. And let's just check with the unit circle for reference to make sure that we have the correct coordinates for 5 pi over 4. 5 pi over 4 is the negative square root of 2 over 2 and the negative square root for 2 over 2 for both x and y. So it looks like we got that one. All right, cool. And let's do another example. How about this one? We'll do one from quadrant 4. Let's find the coordinates for 11 pi over 6. And 11 pi over 6 is right here, which is in quadrant 4. So to find the reference angle for 11 pi over 6, it looks like we have to do 2 pi minus 11 pi over 6. Two 2 pi minus 11 pi over 6 is going to be pi over 6. So we'll take a look at pi over 6 here. And the coordinate points for pi over 6 for x, well, the x coordinate point is root 3 over 2, and the y coordinate point is 1/2. And we can steal that x and y coordinate, and x can be left alone. The x coordinate can be left alone, but the y coordinate has to be made negative. So 11 pi over 6, that's going to be the x coordinate root 3 over 2, and then the y coordinate is negative 1/2. All right, and let's just check our unit circle to make sure that this is correct. 11 pi over 6, root 3 over 2, and then for the x, and then for the y, negative 1/2. Nice, we got it. And this can be done for any point on the unit circle. That same logic can be followed, and that's how you can recover the coordinate points. So that's how you do a unit circle from scratch. And yeah, thank you so much for watching.